what we're going to do today is just prove some cool facts about the relative sizes of different infinities. I picked some examples that I thought would be illuminating, but like if you guys want an infinity that you want to try out, let me know and we can try to sort it. So let me first remind you about the basic tools that we're going to use to talk about infinity. So we're going to say that the cardinality of A equals the cardinality of B, or there are just as many things in set A as there are in set B, just in case there is a 1-1 mapping from A to B. So in other words, if there's a 1-1 function from A onto B. And then this notation means that the cardinality of A is less than or equal to the cardinality to B. And what that means is that there's a 1-1 function from A into B. So there might be some things in B left over. And to assure us that this is good notation, so to assure us that this really does work like an ordering of the right kind, we need this result, that if the cardinality of A is less than or equal to the cardinality of B, and the cardinality of B is less than or equal to the cardinality of A, then A and B have the same cardinality. That result is actually not super hard to prove. I won't prove it just because it's a little bit long and I feel like it would take us half a class and it won't be that illuminating. But if anyone wants to take this stuff seriously, I would recommend trying to prove it. And if you fail, let's talk. And I can give you some hints. It's actually cool. The construction is cool. Not super cool, but cool. OK. So with that in mind, let's start proving some results about infinity. So one thing I thought it would be useful to prove is this. Suppose you have the interval 0, 1, and you have a set which has one thing for each natural number. I'm going to assume that all of these are different, and I'm going to assume that none of them are in here. So these guys are disjoint. So here is a cool result that will be very, very useful. The cardinality of the combined set equals the cardinality of just 0, 1. Does anyone have thoughts about how to prove that? It'll be so simple that when you see it, you'll think, ah, I knew that. Yes?
Just to make sure I understand this, A0, A1, this is just like all the natural numbers, right?
They could be natural numbers. Because I want them to not be in here, and because this contains 0 and 1, it can't really be exactly the natural numbers, but maybe some copy of the natural numbers that isn't in there. Or maybe we can just start with 2. Why don't we start with 2? So let's say that this is this set.
Okay, my first thought, like you'd have to like change the function a little bit, but you take any number in the interval 0 to 1 and you multiply it by okay, so if you were comparing it to like the numbers like 0 to 10 or something, you multiply it by 10 and all of those numbers will be the same. So for this one, it's just you multiply it by like infinity or something, you know, like and you'd have the same number of numbers in both sets.
That is a very nice trick. And there is a certain class of problems for which that trick is exactly what we need. So let me describe that class of problems, and then we'll come back to this, because I think this is very useful. So I'm going to leave this there for now, and now consider this problem, the problem of whether the cardinality of that beast equals the cardinality of, say, that beast. So we have a short line and a longer line. So one way to see that they have the same cardinality is by considering the function that takes f of x to 180x. So that's going to take 0 to 0 and 1 to 180, and everything in between is going to be nicely stretched out. So we've basically proved something amazing. What we've proved is that any closed interval has the same number of points as any other closed interval. Already it's super cool. And we're basically using this trick. We're multiplying in order to expand. Now, that also shows why, if we're to apply it to, in this case, we need to use some care. In the end, we are going to use a version of that. But it's tricky because what happened in the case above is that we sort of stretched out the whole thing. So if we have a function which just consists in multiplying, this is going to stretch out. And this union isn't quite stretching out, because what it consists in is the interval 0, 1, and then just points, 2, 3, 4, 5, 6, and nothing in between. So if we were to just stretch this out, we would overshoot, because we would get all these points in between too. But I like the thought. So it's going to be something along those lines.
Can you just put a decimal point in front of whatever the natural number is?
OK, so no, we can definitely do that. And all those guys are going to live, right? So if we just put a point in front of these guys, they're all going to live in here. So that's fine. But we still need, I mean, it depends what function we use. So for example, supposing we just use the identity function. Then we would definitely hit all these guys. The problem is that then we would have duplicates, because we're using the identity function. So in particular, f of 0.2 equals 0.2. So we take the 0.2 guy who's in there, and we map it to this 0.2. But what about the 0.2 which was in there? That gets nobody mapped into him. So it's like we need to do something to. OK, I'm going to give you guys a hint. So a hint is take our set, and now take this other set. I'm going to call this one A and that one B. So what I want you guys to show is that the cardinality of A union B is just the cardinality of A.
Well, in this case, they're both countable and ordered, so we can just build up A union B by alternating between them, and then map that right to A pretty much directly.
That's exactly right. That's exactly right. So I'm going to say what you said again, but the long version. So That's right. So let's write out A. And let's use the odd members of this set for one thing and the even members of that set for something else. So the odd members of this set, we're just going to we're going to map onto A itself. And the even members, we're going to map onto B. So we're going to take 1 to the first element of A, so 1. We're going to skip this one, and we're going to take 1/4 to the second element of A, which is 1/2. And then we're going to skip that one. And then 1/16 to the third element of A, which is 1/4, and so forth. And then that means that we still have infinitely many things left over, which are freed up to use for B. So we're going to use this guy for the first element of B, which is 2, and that guy for the second element of B, which is 3, and that guy to the next element of B, which is 4, and so forth. So when we're done with that procedure, what happens is that we've mapped each element of A to a different element of the union of A and B, and nobody has been left unmapped. So that's A, and what we have here is A union B. So we have a 1-1 mapping from A onto A union B. Okay, I'm going to pause because this is where all the magic comes from. So all the magic is going to come from versions of this idea. It's Hilbert's hotel. So, this was our hotel, and it was totally full. And then we just basically asked each of these guys to move to room 2 times their old room. So the person in the 0th room stayed, the person in the next room moved, in the next room moved, the next room moved, and so forth.
So what characteristics of A and B allow you to do something like this? Like, I'm assuming it doesn't work for any arbitrary A and B, right?
That's right. So it's certainly not going to work for finite A and B. This particular construction relies on exactly the features that he mentioned. So this particular construction relies on the fact that each of these sets is in effect mapped onto the natural numbers. So we can say for each set what the 0th position is, and the first position is, and the second position is, and the third position, and so forth. Whenever we have that, whenever we have 2 copies of the natural numbers, we can do this.
It seems like there are some infinities where you just go off infinitely in one direction, and some where you're bounded on both sides, but you just go in indefinitely. Is that an important is that going to help us at all?
Nice, nice, nice. Okay, so we're going to start a new detour. This is going to be our final detour. So after this detour, there'll be no more detours. We're going to go back to our original. And I'll remind you where we are. Okay, so Rose's question is important. So suppose, to make it easy, I'm going to do it this way. Take this interval, but without the 1. So it's open on that side. And then take that. So all real numbers greater or equal to 0. Now, as it turns out, those are the same size. So the cardinality of that guy equals the cardinality of that guy. Can anyone show that? So we want a 1-1 correspondence from one to the other.
So the construction I'm used to for this is basically using a I guess in this case it'd be a quarter circle to project one onto the other.
Geometrical proof. Yes! I was going to do something much more boring than that. OK, so a quarter circle. So shall I draw mine, or do you want to try to draw yours?
Basically a line that's equivalent to 0, 1 open but negated. So this.
Oh, no, but wait. Already you have a simpler construction there. Because look, just take this point and consider the set of lines that goes through the circle. So provided that that guy's missing, each of these lines is going to hit exactly 1 point on the little curvy line and 1 point on the line which is infinitely long in that direction.
And then the curved line maps pretty directly to 0.
Exactly. The curved line then just is a twisted version of 0, 1. So the answer to Rose's question is it makes no difference. Yes?
How can there be no gaps, though? Like, I feel like just by the definition of, like, what an angle is, like, as you go to the next line you're drawing, no matter how minute the angle is, as it goes down from this quarter circle to this ray, I mean, it's going to have, like, some gap.
Well, let's suppose it does have a gap. So suppose that, like, that was the gap right there.
Yeah.
Then just consider the line that goes from the origin to the supposed gap. And we'll find that there is exactly 1 point that it crosses. So there can be no gap, because that point is going to be mapped onto that. It's amazing. It's really amazing. In fact, here's something that can be used to drive the point home. So this construction is the most beautiful one. So its beauty will remain unmatched. But just for clarity, to bring the point home, can anyone think of an analytic solution to this problem? So in other words, can anyone just describe a function from real numbers to real numbers? Yes?
We could use the function 1 over 1 minus x.
1 over 1 minus x. And shall we maybe remove 1 from that?
Yeah.
OK. Yeah. OK, so consider that function. OK, so let's look at what that function is going to do. So when x is 0, that fraction is just 1. And we remove 1, so we're at 0. So that function just takes us from the first guy here to the first guy there. And then as x approaches 1, this is going to get bigger and bigger and bigger. And in fact, it's going to get as big as we want. So for any point in here, no matter how big you want it, there is some x close enough to 1 that we're going to hit that point. So nobody's left. This function is a 1, 1 mapping from that guy onto that guy. And there are no gaps. So when I promised weirdness, I meant it. Like, these things really are weird. You can't, in order to know whether you have the same number of points or not, you can't use your intuition. Things that look big turn out to have the same amount of points, the same number of points as things that look small. OK, so let me remind you of where we are. OK, so we've shown that finite intervals have as many points as infinite intervals. We have shown that finite intervals of different sizes have the same points. We have shown that if you have two countable sets, two sets that can be that are 1, 1 correspondence with the natural numbers, then their union has the same cardinality as any of the original points. So now let's go back to our original puzzle. So can anyone prove this? So can anyone prove that if you have this interval and a countable set, that the cardinality of the union of the two is just the cardinality of this interval? And the hint is to use this construction.
So you can extract a countable subset from 0, 1, and I guess we'll use the example on the board where we alternate the terms, and then the remaining terms just map to themselves.
Exactly, exactly. Okay, so the reason I chose this particular set A is because it has the very property he mentioned. So everyone in A on that side of the board is in here. So here's a way to think of it. Here we have the interval 0, 1, and these are the points in A. So 1 and 1/2 and 1/4 and 1/8 and 1/16 and so forth. Those are the points. What we're going to do is we're going to take these points that I just identified and divide them into two groups. The first group we're going to use to deal with these guys. And the second group we're going to use to deal with the set itself in just the way that we did here. So this side of the board tells us the exact recipe whereby we're going to do it. So what's going to happen is that the odd numbers of A, so the points in odd positions, are just going to be mapped onto another copy of the entire set A. And the even members of A, in other words, the points in even numbered positions, are going to be mapped onto the members of our additional countable set. So then what's happened is that that function deals with our distinguished points plus the new set. And then as he said, for all the other points, we just take the identity function. The other points, the points that are not here, just map them onto themselves. That combined function is a 1-1 mapping from that onto that. Okay, so here's my plan. I'm going to sit down. I will await a question. And if I don't get a question, I'm just going to say that again so that to make sure that people understood it.
How do you gonna write this function in terms of fx as you did before?
That is a good question. I actually wrote it out before coming here. I wrote it out for a more general case, so I'm going to state the case I wrote it out for to make it clear. So what we're going to show is that there's a 1-1 correspondence F that takes us from that set to this set. And I'm just going to assume that the two are disjoint. So the problem we're dealing with is just a special case of this problem here. So then here's how to do it. So the function is going to treat points in here differently, depending on whether they're of the form 1 over 2 to the n or not. The points that are of this form are exactly the ones that we selected. For the ones that are not of that form, our function is just going to be the identity function. For the ones that are of this form, what we do with them depends on whether n is even or odd. If it's even, then we're just going to take 1 over 2 to the n to 1 over 2 to the 1/2 of n. So when n is 0 and this number is 1, that's going to take us to 1 again, because 0/2 is 0. When n is 2, so this whole guy is 1 over 2 to the 2, in other words, 1/4. That's going to take us to 1 over 4/2, 2 to the 4/2, in other words, 1 over 2/2, which is just 2, 1 over 2, and so forth. And when n is even, that number is going to be taken to one of the a's. So for example, when n is 1, that's going to take us to 1 plus 1 divided by 2, 1, so a1, the first of our a's. When n is 3, it's going to go to the second of our a's. When n is 5, it's going to take us to the third of our a's, and so forth. So what we need to check is that this function sends everyone here to someone and only to one person. But of course it does, because everyone in here is going to have one of these 3 forms, and it gets assigned to a unique person. And then we need to check that everyone in there got assigned someone. But that's true too, because all of the a's are going to be covered by numbers of this form, and there are enough of them. All of the things in here, which are of this form, are going to be covered by these guys, and there are enough of them. And everyone here who isn't of this form is going to be covered by itself. I see faces of bamboozlement, faces of pain, and faces of satisfaction. That makes me happy. Those are the 3 stages. So shall I continue? Shall I? Okay. Now the reason I wanted to prove this little result is because it simplifies the proof of the thing that I really wanted to prove. And that is this. The first time I read about what I'm about to say, it was worse than bamboozlement. I just thought that there had to be some kind of mistake somewhere. So one can show that the number of points on a line equals the number of points on a square. So there are as many points here as there are there. Not just the edges, but the entire area of the square. Okay, and here's how we're going to prove it. So a useful way of thinking about the points in the 0, 1 interval is just as sequences of that form. So everyone in there has a description of that kind. And the points in the square are just pairs of sequences of digits of this kind. So the way I'm going to prove the result is by first thinking not about the points themselves, but about just their notations in this base 10 way of writing things out. And then there's a little annoying problem, which is that, as we've seen, there are points in there that have more than one notation. So for example, the half point there can be written out like that, or like that. So we're going to have to do something to correct that problem. But what we're going to do is we're just going to use this trick. That's what I wanted to prove. OK, so what I invite you to do is to forget about the complication that I just mentioned and just think that what we're showing is that the set of sequences of this kind is in one-to-one correspondence with the set of pairs of sequences of that kind. So I'm going to write that out. So let the set S for sequence be the set of sequences D1, D2, D3 for these digits. So S is just the set of infinite sequences of digits. And what we're going to show is that the cardinality of S equals the cardinality of its product. And showing that is amazingly simple. Can anyone think about how to do it? It's like this tiny trick. And if you get the trick, then there's nothing to it. Yes.
To go from S to S cross S, however you say it, you take like every other digit of S and you like make it one thing and the other one's in, yeah. And to go backwards, you can do the same thing. You like spread them up and then do that. You can explain that better now.
Exactly. Yeah, so let's do it the reverse way you mentioned, because I think it's slightly easier. So we're going to take a function f that takes us from each element in there to an element in there, and which is 1-1 correspondence. So what f does is we give it a member of S cross S. So in other words, a pair of sequences. So it's going to be something of that form. Two sequences, and it delivers this sequence. We just take the first element of the first one, followed by the first element of the second one, second, third, fourth, and so forth. Oh, sorry, because, oh, what? Thank you. That was just a test. Sorry about that. Thank you. So now let's check that it works. So we need to see to check that it works is first that this function is defined for every element of S cross S. And of course it is, because whatever two sequences you're given, the result of alternating those sequences is going to be well defined. It's also unique. So if you're given two sequences, there's only one sequence that can result from alternating. OK. Then the next thing we need to check is that using that technique, you hit everyone in here. But of course you do, because everyone in here is going to have some sequence. And that's going to result from alternating two sets. Which ones? Well, the one that consists of all the odd entries and the one that consists of all the even entries. So our function goes from here to here. It's 1, 1, and it's unt. OK, now I'm going to correct the little problem. And don't worry if you don't understand this. So think of it as I've opened a parenthesis. I'm going to very briefly say how it works, and then I'm going to close the parenthesis. So parenthesis open. We get a problem because S and S cross S aren't really 0, 1 and 0, 1 cross 0, 1. You have some extra things in here because you have two different sequences. For example, that sequence and that sequence that correspond to the same point up there. But that is not something we need to worry about, because the only case in which that can happen is the case in which we have some number in there which has a decimal expansion ending in zeros or ending in nines. All of those numbers are rational numbers. And we proved last time that there are as many rational numbers as natural numbers. So that means that our set of problem cases is just a countable set, which means that we could just use this theorem to show that the result of adding problem cases doesn't change the cardinality. So the way we solve our problem is we first show that if you go from that interval to S, you preserve cardinality. Then we show that if you go from S to S product S, you preserve cardinality. And then we show that if you go from here to there, you preserve cardinality. So you preserve cardinality if you go from the line to the square. Close my parenthesis. And notice that this result generalizes. So we could use the exact same procedure to show that there are as many points on a line as there are points on a cube or a hypercube. Or I didn't even know the notation after that, like a hyper duper cube. In fact, you can even do it for the analog of that in countably many dimensions. And by using Rose's observation that you have as many points in there as you have in there, you can extend these results to not just line segments and squares and cubes, but the entire line, the entire space R2, the entire space R3, the entire space R4. OK, so look where we are. So what's happened is that we've been focusing on two sizes of infinity. So we have the size of the natural numbers, which includes the natural numbers and also all the integers, so positive and negative, and also the rational numbers. And that was like one big class. And it's kind of hard to escape that class. But we showed last time that you can escape it if you go to the real numbers. So you can escape it if you start focusing on all the real numbers or indeed segments. And then we reach this new class, which is bigger than the class of natural number infinities. And again, it's hard to escape. So you can't escape it just by moving from finite segments to infinitely long segments. And you can't escape it by moving from R1 to R2 to R3 to R4 to R5. So we're stuck again. And it's reasonable to wonder whether we'll be stuck forever. So maybe you only have infinities of those two sizes, or whether you can become unstuck. So the last thing I want to prove today is that you can always become unstuck. So for every set, there is a bigger set. And that's the fundamental theorem of the field, and it's due to Georg-Cantor. OK. So what we're going to show, the cardinality of a set, any set you want, is not the cardinality of the power set of that set, where the power set of a set is just the set of all subsets of that set. So for example, the power set of that guy is yes. Yes. Thank you. Another test. Thank you. Now, we know, of course, that the cardinality of this guy is going to be smaller or equal to that guy, because it's very easy to define a 1-1 function from here into there. Just pick the function that takes every element of your set to its singleton. So we know this. And from those two things together, you get that the power set has strictly more elements than the set. OK, so here's the proof. So take A. That includes a bunch of things, possibly infinitely many things. And then take A's power set, which includes a bunch of sets. Which are all composed of elements of A. And we're going to proceed by reductio. So we're going to assume the opposite of what we want to prove and derive a contradiction. So what we want to prove is that there are more things in the power set than in A. Yes?
That only works if set A is not empty, right?
Set A is not empty? No, it even works when set A is empty. And I can verify that very easily. So if A is empty, then its power set is the set containing only the empty set. So whereas that has 0 members, that has 1 member. So the power set is bigger than the empty set. That's the beauty of it. It works for every set. It can be empty, it can be non-empty, and it can be infinite. OK. So we want to prove that there are more things down here than up here. So let's assume the opposite of that for reductio. If we assume the opposite, then there has got to be a 1-1 function f that maps all the people on the top to someone, and exactly one person on the bottom, and there's no remainder. So every set down here is mapped onto someone. OK. Well, if that's true, then we can define the set R which consists of all things in A with a property that they are not in the set they get mapped onto. So, it might happen, for example, suppose that you have a thing A in there, and maybe that gets mapped onto this guy, which includes A amongst other things. So A gets mapped onto a set that includes it. So because we want R to be the members of A that don't have that condition, we know that our little a is not going to be in R. On the other hand, someone over here, maybe D, is going to get mapped onto the empty set. So D is not a member of the empty set, so D is going to be in our big set R. And now, just ask yourself this question. Apply the inverse of f to R, and by assumption that has to be well defined, because everyone down here was mapped to someone. And ask yourself, is that guy who's a member of A member of R? If it is a member of R, it has to have this property, the property of not being inside the person he's mapped onto. But we're assuming that he is. And if he's not, then he has the property that it takes to be in R, so he should be. So this guy is in R if and only if it isn't in R. And that's a contradiction. So we were able to prove a contradiction from our assumption that this 1-1 function from A onto its power set exists. So it can't exist. And if it doesn't exist, the power set is bigger than A. I spent 2 years of my life trying to show that that proof was incorrect. No, it is correct. See you next week.